Hello, everybody. It's time. We're going to start book 2. So our first topic is called anti-differentiation, or the inverse of derivatives, or the real word that we use, integration. So indefinite integration. We'll talk about exactly what this means in just a couple minutes, but big deal here is we've been taking derivatives all year. So we have something like x to the fourth. And if we take the derivative, so if that's y, and we said y prime is equal to 4x cubed, right? So here's what an antiderivative is. We start with y prime. Let's say we start with 4x cubed. Well, what did I take the derivative of to get 4x cubed? Oh yeah, I took the derivative of x to the fourth. And that's, yeah, it's gonna take the rest of the year for us to kind of flesh this out and see where it goes. Yeah, okay. So here we go. All right, so the notation that we use for this is if I want to take 4x cubed and I want to take the antiderivative of it, what I do is I slap this symbol on the front, kind of looks like an S, and then I put a sandwich on the other end. You know how when we take derivatives with respect to a certain letter. We take derivatives with respect to x or with respect to time. So after this, I let the integral know, hey, I want to take the derivative with respect to the variable in here, and the respect to the variable here, let's see, the variable I care about is x, so it's dx. So this would be we're going to take the integral of 4x cubed dx is how we would read that. So this is called an integral sign. So the thing is, the integral of 4x squared, or 4x cubed, the thing that I took the derivative of to get 4x cubed, I took the derivative of x to the fourth. But pause. Is there something else I could take the derivative of and get 4x cubed? Yeah, there's lots of things. I could say x to the fourth plus 1. What's the derivative of this? 4x cubed. I could say x to the fourth plus 1.01. I could say x to the fourth plus pi. I could say x to the fourth minus 100 million. Sure, the derivative of all these things is 4x cubed. So each of these is an antiderivative of 4x cubed. So when we do what we call indefinite integration, instead of saying, oh, it's this one, this, instead of saying it's one of these in particular, we say it's x to the fourth plus some constant c. And this constant is arbitrary. The word arbitrary means it doesn't really matter what it is. It's like, it's something, it's some number. It doesn't matter. So sometimes we find out what C is to make it what we call definite integration. But yeah, so that's the basics of what integration is. So let's look at some examples. All right. All right, so let's see. I think it's visible enough for me just to do it in the book today, isn't it? Okay. So we got a new, when we ordered these books, we found an easier way to get them to print nicer. So hopefully they'll come up nicely in the videos. So we want to take these integrals, or perform these integrals. So what did I take the derivative of to get 7? So there's something where the derivative is just a plain number. Oh yeah, just plain x. So we would say the integral of this is 7x. But then it could be 7x plus 3, 7x minus 100, whatever. So we say 7x plus c. Anytime I forget plus c on this page, I've got 14 more chances on this page to forget, really. So, all right, let's keep going. X to the fifth. Okay, so, well, what did I take the derivative of to get x to the fifth? Well, x to the sixth, right? So let's just double check that. So if I was to go back and look at the first one again, we get 7x plus c. Well, if I take the derivative of that, I get 7, and the c turns into a 0, so we're good. This one, if I have x to the 6th, if I take the derivative of that, I get, oh shoot, I get 6x to the 5th. So x to the 6th actually is not an antiderivative of x to the 5th, because this 6 pops out when we take the derivative. So what we're going to need to do is we're going to need to play with this a little bit to make it work. And it turns out if we just were to say it's 1/6 x to the 6th. Let's see what happens now. Take the derivative, there's 1/6 x to the 5th, and we multiply by a 6 out front. What's 6 times 1/6? They cancel out. So another way people will write 1/6 x to the 6th is they'll write x to the 6 over 6. This is a very common way to do it. And so you might notice that no matter what power we start with, if I start with x to the 50th, its integral is going to wind up being x to the 51st divided by that new power. So for me, when I teach my students, a lot of times I'll say, so whatever that power is, instead of multiplying it by the front, so what we used to do with derivatives is we would multiply by the number and then subtract 1, and that equals new exponent. So inverse operations happen in reverse order. So instead of subtracting 1 to get the new exponent, we're going to add 1 to get the new exponent. And then instead of multiplying by the number, we'll divide by the number. So notice how subtracting by 1 switched to its inverse operation, and multiply switched to its inverse operation, and the order that we did them reversed. So it turns out this is x to the 6 over 6 plus c. Let's see. Let's look at the next one. X to the 12th. X to the 12th. So that's going to go, following this pattern, we're going to get x to the 13th divided by our new exponent of 13 plus c. And remember, the reason why these work is because if I just take the derivative of this, I should get what I started with. So, oh, now we're getting into some real dense problems. Number 4, x to the 4th minus x squared. All right, well, if you remember how derivatives work, derivatives are just term by term, right? And so integrals are also just term by term. We can look at this x to the 4th, and I can rewrite this, or when we take when we take the integral of this, we can say this is x to the 5th over 5 minus x to the 3 over 3 plus c. That's it. Okay, number 5. Hey, it has t's now, but see how it says dt? The variable that we're integrating with respect to is still the variable in here. So it works the same way. We're going to add 1 to the exponent, t to the 4th over 4, plus t to the 2 over 2, plus, oh, that's a plain number. So that means the integral of that's just going to be t, plus c. So I'm hoping that this isn't too fast. There are a bunch of rules at the top of the page, but I would rather kind of intuitively get to them. These are all kind of something we can think about. So, of course I say that, and then number 6 has our first kind of real rule, and that it works very similarly in derivatives. Like if we had x to the 4th and we were taking the derivative of x to the 4th, we'd get 4x cubed, right? And then if we were taking the derivative of 9x to the 4th, the only difference is this is still going to be 4x cubed, but then we just multiply that 4 by 9. So it's going to be 9 times 4x cubed, or just 36x cubed. And most of us do that really quickly in our heads. And so with this, it's no different. This one says the integral of 3x cubed dx. I can say this turns into 3x to the 4th over 4, and that's totally fine. Plus c. Another option though is, since it's a constant times our our function, we could actually pull a 3 out and say this is 3 times the integral of x cubed dx. And in this situation, it doesn't make it any easier or harder. But then I could say, so this is 3 times x to the 4th over 4 plus c. Works out exactly the same way. So, let's see, 3x to the 4th over 4 plus c. It's really a matter of, for this problem at least, a matter of preference and what's going to feel simpler for you. So now bring it into more examples. We have 2x squared, so I can take the integral and get 2x cubed over 3. And then here there's an exponent of 1, so we'll add 1 to that exponent and get minus 7x squared over 2, then minus 8x plus c. So yeah, whatevs. And even in something like gross looking, like number 8, I'm actually going to do this on a separate piece of paper. I want to make sure there's enough room. So we've got 2/3 x to the 5th minus 7/3 x to the 3rd minus x squared over 4 dx. All right, so if I'm taking this integral, let's see, you can essentially almost, you can right off of the screen, you can ignore the coefficient and just go, okay, this is 2/3, and then what happens here? Well, this is x cubed. Nope. 5 plus 1 is 3. All right, so x to the 6 over 6. And we're going to simplify this in just a minute. Minus 7/3. This one will be x to the 4th over 4. And then this one is going to be x to the... there's a 1/4 out front of this one. And then we'll have x to the 3 over 3. Plus c. So now when we clean this up, we'll see 2 and 6 can turn into 1 over 3. 7, 3, and 4 don't have anything in common. 3, okay, so now I'm going to say this is x to the 6th over 9, because 3 times 3 is 9, minus 7x to the 4 over 12, minus x to the 3rd over also 12. Oh, plus c. So maybe, well, that's x to the 4th, that's x to the 3rd, so it doesn't really look like there's anything more we can do beyond that. You might prefer, instead of writing the fractions like this, you might prefer to say 1/9 x to the 6th minus 7/12 x to the 4th minus 1/12 x to the 3rd plus c. These are identical. They're just alternate ways to write, or they're functionally identical. They're different ways to write the same thing. So, all right, number 9. Ew. 9 I'm also going to write off to the side so we can talk more about it. Now this is not e to the x, this is e times x plus 1 over e. This looks so bad. So bad. But this is just a number times x. So that means that it's antiderivative, it's integral. We're going to add 1 to the exponent, get e times x to the 2, and then divide by our new exponent, divide by 2. This one, 1 over e, that's a number. It's a constant, so it's going to be 1 over e times x. Gross looking, but like when you think about it, take the derivative of this, you'll get 2e times x divided by 2, and the 2's will cancel, plus the derivative of this is just 1 over e, and that's what we started with, plus c. So that's the big deal going on with these things. And of course, we have to start mixing it up and looking at more thought-provoking examples. So number 10. Number 10, we have 1 over x squared dx. If you know where this came from, its antiderivative is easy. Oh, see, it's so easy to put me to sleep. No, but let's say you're stuck and you're not sure what's going on. Well, just remember, this is x to the negative 2 dx. So now I can use that same idea of adding 1 to the exponent, get x to the negative 1 and then divide by my new exponent of negative 1. So I could rewrite this. Oh, that drops down to the bottom, right? So it's going to be negative, and we can say negative 1 over x plus c. And then number 11 is just more of the same. So I'm actually going to use an alternate strategy for number 11 to talk through how I do these for real. Because for me, I don't always like to rewrite here. Instead, I like to kind of rewrite in my head and think about it. So this is 2 to the negative 3. Or sorry, 2 over 2x to the negative 3. So when I take the integral of this, instead of writing 2x to the negative 3 and actually thinking about that, I know this is going to be 2 over x to the 2, right? 2x to the negative 2. And then I'll have to divide by my new exponent of negative 2. And so I'll divide by it, and that'll be on the bottom. Similarly here, and I'm not really going to care about this minus sign. Something might happen to it, something might not. Something's going to happen, but let's just pretend we don't know that. So the 5's still there. This changes to x to the 3, right? Because we're adding 1 to that negative exponent. And then I'll have to divide by my new exponent of negative 3 plus c. So then we can kind of clean this up. The 2 and the 2 cancel. We'll have negative 1 over x squared plus 5 over 3x cubed plus c. That's my integral. So just in case that was too much, again, what we can do is we could rewrite this and think about this as 2x to the negative 3 minus 5x to the negative 4 dx, and we can get 2x to the negative 2 divided by negative 2. Like, we add 1 to that exponent, divide by the new exponent, and then minus 5x to the add 1 to that, get negative 3, and divide by the new one. And then, do our simplifying, so these cancel and we get negative 1. So negative 1 over x squared plus 5 over 3x cubed plus c. So we get the same answer, different strategy. It's really whatever is going to be comfortable for you. Then we get to the dreaded number 12. Number 12 is the integral of the square root of x dx. I don't want to just jump to the answer on this one. We got to make sure we talk about this. This is x to the 1/2. So the integral of this means we're going to have to add 1 to this exponent. X to the plus 1. So 1/2 plus 1, well, that's going to be 2 over 2 to 3 over 2. So what number are we going to divide by? We're going to divide by our new exponent. But writing over 3 over 2 is kind of weird looking. So instead of dividing by this fraction, we could multiply by its reciprocal. So instead of dividing by 3 over 2, we could multiply by 2 over 3 plus c. So think with me now. Let's take this derivative, 2/3 x to the 3/2 plus c. When I take this derivative, the 3/2 comes out front. We get 3 over 2 times 2 over 3x. Subtract 1 from that, we get 1/2. The c turns into a 0. 3/2, 2/3 cancel out, we get 1. We get x to the 1/2. So that's how that works. And so one way that people will think about these is they're going, okay, how do I cancel out? Oh, excuse me. Cancel out the coefficient that's going to be up front. So anyway, I got 2/3 x to the 3/2 plus c. And this is not something I have memorized. I don't have almost any of these derivatives memorized, or antiderivatives memorized. It's I understand the patterns, and we try to link up the patterns and use them. So there are some antiderivatives that we're going to completely memorize in this class, but most of them are going to be something that we develop every time. So like 13, looks like a train wreck, but it's not going to be that bad. All right. So we got 2 cube root of y minus 4 fourth root of y dy. So just wanted to rewrite it so I could use this side paper and write things out. So let's see. Oh, I did not get enough sleep last night, clearly. All right, so I'm not gonna do the full lesson today, especially because I'm so tired sounding. We're just gonna finish this page and then we'll go from there. So part 2 will be coming soon. So let's see, 2 cube root y, that's gonna be 2, let's see, the integral's still there, haven't taken the integral, 2y to the 1/3 minus 4y to the 1/4 dy. And so when we add 1 to our exponents as we integrate, we'll get 2y to the 3/3, right? Plus 1. 2y to the 4/3, and then I'll multiply by the reciprocal, 3/4. Minus 4y to the, add 1 to that, that's 4/4, so 5/4. And then multiply by the reciprocal of that, plus c. So we'll get, well, let's see, 2 and 4 cancel to 1/2, so 3/2 y to the 4/3 minus, nothing cancels here, 16/5 y to the 5/4 plus c. So then 14, it's just, these are good exercise for our brains. Another way to put it, these are good exercises for our brains. So 14, I'm actually just going to rewrite it to start. This is 1 over x, 1 over the square root of x, which is 1 over x to the 1/2. So this is x to the negative 1/2 exponent minus x to the negative cube root of x squared. That's going to be 2/3. Remember, the index goes on the bottom, the power goes on the top. So with that, now it's, straightforward. We add 1 to this exponent. We get x to the 1/2, and then divide by the new exponent. Divide by 1/2. Multiply by 2/1. And then here we'll add 1 to the exponent. So we'll get minus x to the plus 3/3. We get to the 1/3. Multiply by the new reciprocal, which is 3/1 plus c. So I could rewrite this as 2 root x minus 3 cube root x plus c. So in some ways it's kind of like someone's giving us all their answers to a test, but we don't know what the actual questions are, and so we're going and finding the question. And in that respect, you can kind of think about integrals as being little puzzles. Ooh, I like puzzles. All right, let's see, 15 integral x to the 2n plus n root pi dx. N is not equal to 1/2 negative. Okay. Hey, guess what? N's a number with respect to x in this integral. N is just any number we want. So what that means is that if I'm trying to find the integral of this, we're literally, okay, I'll just do it, and then if it's, I'll maybe do another example to kind of help you see what's going on. So x to the 2n, well, so we're going to add 1 to that exponent, right? So we're going to get x to the 2n plus 1. We don't know what n is, but we're taking the integral with respect to x. So if this had been x squared, it would be x to the 3rd. If it was x to the 50th, it'd be x to the 51. So this is x to the 2n. I don't know what that is, but 2n plus 1 is going to be our new exponent. And so we're going to divide then by 2n plus 1. We're going to divide by our new exponent, which looks really weird. But that's why they told us n couldn't equal -1/2, because if n equaled -1/2, then we'd have a problem here. But hey, n root pi looks really scary. N's a number. Pi is a number. Number times a number, it's still a number. So what's the antiderivative of just a number? It's that number again with an x tacked on the end. And that's it. So as awful as this seems, it's like, oh, it's just if x is to some power, then you just add 1 to the power, divide by the new power, plus the integral of some number. Oh, just slap an x on it, throw a plus c on the end. Boom, that's it. Cool. So if I look at the homework questions, besides knocking over the camera, it's like this whole first page is essentially manageable, especially the first 13. If you look here, 14, it's got this x minus 9 squared. You know what, let me just, no, for the interest of time, we're going to stop there in this video, but in class we'll probably handle it tomorrow, so I'll need to film a little bit more. Well, hey, welcome to book 2. Hope this was helpful, and I'll see you soon. Bye!